This is the bits, bytes, and hexadecimal activity. This is not language specific, so this will be for all 4 languages because this is really about computers themselves. So we want to learn about bits, bytes, and hexadecimal numbers. I definitely encourage you to do a little research on your own, either before or after this video, to dive into it a little bit better. But we basically want to run through this, and I'm going to open up a little scratch pad here in Visual Studio Code, and we'll kind of run through some of these activities. So let's start off with bits and bit fields. So our numbering system, our normal numbering system, is base 10. So in other words, we have 10 characters before we move on and increment the next one. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. To go to the next number, we reset 9 back to 0 and add a 1 to the tens digit. So 1, 0 is 10 in our numbering system, which makes sense. We're kind of used to that. Bit fields are based on a base 2 numbering system. So in other words, the only values we have are 0 and 1. In order to increment past 1, you reset the 1's place back to 0, and you add a 1 to the 2's place. So 2 in binary is 1, 0. So bits only have 2 values, 0 or 1. They represent off and on respectively. Bits are kind of an abstract way to reflect electrons on a wire. So as electrons are being transmitted on the wire, and as we read those electrons, or the absence of an electron, that'll tell us if there is an electron, it's a 1. If there is no electron, it's a 0. Similarly, magnetic fields on a section of a physical disk, how spinning hard drives work, if there is a magnetic charge, that represents a 1. There is a charge. If there is no charge in a sector, that means it's 0. So this is how we actually represent data in computers themselves. So bit fields are basically collections of bits organized together to represent a number. I've got some instructions here on how to do this in general. I recommend reading through this. I'm going to jump down and start looking at the example here. So let me open up a new panel, and I'm going to open up a little scratch pad here, and we're basically going to do this example. So we want to calculate 100 as a bit field. So 100 in decimal is what as a bit field? That's what we need to figure out. So to do that, we're going to arrange the powers of 2, and I'm going to do them from largest to smallest. I'm going to actually go up just a little bit above 100. So the largest power of 2 is 128, and then 64, 32, 16, 8, 4, 2, and 1. It's a little easier to list these out if you don't know them by starting at 1, and you simply double from there. So 1 times 2 is 2, times 2 is 4, times 2 is 8, 16, 32, 64, and 128. I've just arranged them from largest to smallest instead, because this is the way we're going to arrange the digits in our final number. So there are 8 digits here, so 1, 2, 3, 4, 5, 6, 7, 8 places that we're going to have values, and each one of these places is going to be a 1 or a 0. So what we have to figure out is for each of these places, does it fit into the remaining number? We're going to subtract from 100 as we find values that fit. So starting off, 128, is that less than or equal to 100? The answer is no. So the first digit is 0. It does not fit. The next digit, 64, is it less than or equal to 100? The answer is yes. So our next digit is 1. Because we have a 1 here, we need to subtract that value from 100. So we take 1 times 64 and subtract that from 100. That leaves us 36. So 36 is the remaining number we have to represent with the rest of the digits. The next digit is the 32 place. Is 32 less than or equal to 36? The answer is yes. So the next digit is a 1. 1 times 32 is 32. So we'll say minus 32. That leaves 4 as our remainder. Is the 16 digit less than 4? The answer is no. So the 16th place is 0. Is the 8 digit less than or equal to 4? The answer is no. So the 8 digit is 0. Is 4 less than or equal to 4? Absolutely. So the next digit is a 1. 1 times 4 is 4, so we will subtract 4. That leaves 0. Because there's 0 remaining, that means the remaining digits are also 0. Nothing else fits. So we can say 0 and 0. So the final answer on 100 represent as a bit mask or a bit field is 0110, 0100. You may see them all together, or you may see a space between the groupings of 4 digits. But 01100100 is the binary value of 100. Very wordy. But these represent, if these were wires, if these were 8 wires, they would represent things going along. It would be no electron, 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 no electron, no electron, electron, no electron, no electron. So 8 wires. As the data comes across those wires all at the same time, if there were electrons on the 2nd, 3rd, and the 6th wire, that would represent the number 100 to the computer. So that's how the binary values work. Now let's go back the other way. So we're going to find the base 10 value of a bit field. So again, we're going to start off with a number. So we'll say 10101 is what in decimal. So we're going to go back the other way. So looking at these values, there are 5 places. 1, 2, 3, 4, 5. So our placeholder values are 16, 8, 4, 2, and 1. Basically, we need to take each of these placeholder values and multiply it by the value in that place. So the first one is 16 times, there's a 1 there. We're going to add to that 8 times, there's a 0 there. Plus 4 times, there's a 1 in the third digit. Plus 2 times, there's a 0 in the fourth digit. Plus 1 times, there's a 1 in the fifth digit. So let's simplify these. We've got 16 plus 0 plus 4 plus 0 plus 1. Do quick math, that's 21. So 10101 in binary is the number 21 in decimal. So we're just going back and forth. That takes us through binary. So let's switch gears now to talk about hexadecimal numbers, and I'll open up a new scratch pad for this. So hexadecimal numbers literally mean 6 and 10 numbers. In other words, 16 values. They're simply numbers that use base 16 instead of base 10. So our numbering system only has 10 digits, 0 through 9. So we use the first few letters of the alphabet to go past 9. So in other words, once you get to 9, I'll just list these out. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. To represent 10 is A, 11 is B, 12 is C, 13, 14, and 15. Once we get to the very end, to increment, we're going to reset this back to 0 and add 1 to the next place. So 16 would be 1, 0. And then so on. 11 in hexadecimal is actually 17, 18, 19, 20, and so on. So that's how hexadecimal numbers work. So each position has a value between 0 and F. So again, A is the same as the number 10. F is the same as the number 15. Oftentimes, we'll see hexadecimal numbers grouped into groups of 2, 4, or 8 characters. So maybe A, D, or C3, or 1, or 1F, right? Or you might see 3, 2, C4. Oh, and actually, that's 4. I need one more. Let's do 0, 0. There's 2, or you might see FC, right? So groups of 4, groups of 2, groups of 1. These are common ways to see hexadecimal numbers represented. So again, we've got the ways to calculate a hexadecimal number. I'm going to jump down and go ahead and start looking at the example. So if we want to get the value 100 as a hexadecimal number, what would that be? So again, we're going to list out the placeholder values, and they are 16 and 1. So the left digit is the 16's digit, so it's 1 times 16. The right digit is the 1's digit. So let's start off, we're going to have 2 placeholders. We're going to start off, we're going to say, does 16 go into 100 evenly? Yes, it does. It's less than or equal. How many times does 16 go into 100? Turns out it's 6. So 6 times 16, we're going to need to get the remainder again, or the difference. So we'll say minus 96. 6 times 16 is 96. That leaves 4. So our 1's digit is 1 less than or equal to 4. Yes, it is. How many times does 1 go into 4? 4 times. 4 times 1 is 4. Let's just confirm that we do end up with 0. So 64 is the hexadecimal number for the binary or the decimal number 100. So there's our example of going from decimal to hexadecimal. So let's also go the other way. So we're going to find the base 10 value of a hexadecimal number. So we're going to start with the number AF. Yes, that is a number. So AF is what in decimal? So again, we've got the 16's place and the 1's place. So we're going to say 16's place times the value of A, which is 10. We're going to add to that the 1's place times the value of F, which is 15. So 16 times 10 is 160. 1 times 15 is 15. Therefore, 175 is the final answer. So AF equals 175. So we've converted back and forth on the hexadecimal side. All right, let's switch over to bytes. Bytes are a collection of 8 bits. And we saw this here, right? So these are 8 bits, so this also represents a byte. So it's a collection of 8 bits. Bytes are often represented in 3 different formats. Decimal, base 10 normal numbers. Bit fields, 8 digits that are 1s and 0s. Or hexadecimal numbers. So AF, for example, is a byte. Bytes will range from 000000000 to 11111111. Or from 0 to 255 in decimal, or 00 to FF in hexadecimal. Bytes are often stored together as words. Words are not what you and I think of as words. A word is a grouping of numbers or grouping of bytes together that represent a larger numeric value. The most common word that we use is a 32-bit integer, a whole number that uses 32 bits, meaning 32 bits are 4 bytes. So 32 bits divided by 8 bits in a byte is 4 bytes. The order of the bytes in a word are important. So for example, 0000000F could be 15 if we use something called big endian. Or it could be 251,658,240 in little endian. The question is this left side, is this the smallest value or the largest value? In general, most systems are going to use big endian. We're used to big endian because our numbers are big endian. right? The far left is the 100 millions place, and then the 10 millions place, and then the 1 millions place. So we're used to values decreasing as they go from left to right. So big endian is normal. Normally we would read this as 15, but any system could decide to make this little endian, and we need to understand that. Generally, you don't have to worry about endianness for most programs that we do. It does come up from time to time. So if you find that you're getting really strange numbers and you're getting data from some other computer, there could be an endianness problem that you need to reverse on. That's basically it. So the last thing I want to cover really fast in this exercise or this activity is we've gone through this manually. I want to show you the shortcut. I want to show you the easy way to do this, and that is the calculator application in Windows. So if I just type calc, open up the Windows calculator application, I can use the Windows calculator to do the conversion for me. Don't do it by hand. Let's do a couple of these real fast. So in the calculator app, I'm going to hit the hamburger menu, and I'm going to open up the programmer function. So you're going to switch from standard to programmer function. It's going to change the layout a little bit. And here, the mode is going to be the mode of input. So these are the numbers I'm typing, and then it's going to show me the values. So example, if I want to say what is 100 in binary, I need to make sure decimal is selected because this is a decimal number. I'm going to type 100, and it gives me the answer down below. And I can click on it to get a little zoom in, and we'll see 0110, 0100 is the same value that we calculated. Alternatively, if I want to go back the other way, so again, here is 10101. I'm going to switch to binary mode, 10101. And notice in decimal, it is the number 21. So calculator is going to do that for you. So if you need to do that by hand, do not do it by hand. Do not do it in your head. Use calculator to make sure you're doing the math correctly. Let's also look at the hexadecimal numbers really fast. So if I wanted to know what 100 is, again, I'm going to go to the decimal entry mode, type 100. Sure enough, the hexadecimal value is 64. Similarly, to go back the other way, I type AF in hexadecimal mode, and we'll see the decimal number is 175. So again, if you ever need to go back and forth between hexadecimal, decimal, or even octets and then binary, use the calculator app. When you open it up, make sure to change the mode to programmer, and then when you're done, you can change it back to standard. That concludes our bits, bytes, and hexadecimal activity.